My name is Gail Schaefer, and I'm the director of the CHARA Array. The CHARA Array operates 6 1-meter telescopes that are spread across the mountaintop up here at Mount Wilson Observatory. We have a staff of about 15 people here. And the majority of the people who work up here on the mountain have a functional job where they provide some operational support for the array, whether it's supporting observations during the nighttime of making sure that all the telescopes are pointing, the cameras are running. And we also have daytime staff that's in charge of making sure all the optics in the lab are aligned so that we can actually get these interference fringes at the nighttime. And just maintaining computer systems and all that. And so, so each staff position up here, each person works majority of the time just supporting the operations of the array. But usually maybe about 20% of the time is carved out for research. Basically, the goal of the CHARA Array is to get very high angular resolution so you can get images of stars and their environments. And so basically, the bigger you can build the telescope, the higher angular resolution you can get. There are limits to how big you can build a single telescope. So what we do at the CHARA Array is that we have 6 small telescopes that are spread across the mountaintop, and we bring the light together to simulate a telescope that is 300 meters in diameter. So this gives us a very high angular resolution to image the sizes of stars and image their surfaces. What we do at the CHARA Array is that we collect the light on each of the 6 telescopes, and then we send the light through vacuum pipes into a beam combination laboratory. And inside the laboratory, we have carts that move on rails, and basically they track the star so that the light from each telescope travels the exact same distance, down to a fraction of a micron. And from the carts, we send them into a beam combination lab, and the light is combined by one of several instruments we have in the lab. Instead of getting direct images of stars like your classical telescope might, what we actually do is we interfere the light from multiple telescopes together. And so what we get is an interference pattern. And basically these interference fringes encode the spatial structure of the you're looking at. So they include information about the size and shape of stars and any features on their surface. Our science goals are basically to measure the sizes of stars, and this is important for just understanding how different types of stars evolve throughout their lifetimes. And we also can image very close companions to stars, and also image their circumstellar environments. So young stars that form with circumstellar disks around them, we can peer into the inner regions of those disks and study the structure of and eventually these disks will be the sites of planet formation. And we can actually get detailed images of stars too. So stars that are magnetically active, we might see star spots on their surface, and we might also see convection cells on the surface of supergiant stars. And there's also a lot of work on mapping the orbits of binary stars, so 2 stars that are very close together. And so as you map the orbits of the stars, if you measure the angular separation and their period of how long they go around each other, it's a way to get the masses of the 2 stars in the system. And so basically the mass of a star determines how it evolves throughout its lifetime. So this gives you a lot of information on just the fundamental properties of stars and how they evolve over time. High angular resolution astronomy is what the CHARA Array does. Basically, when you go from the infrared to the visible light, you get even higher angular resolution when you go to smaller wavelengths. So this will open the door for us resolving and getting images of even smaller stars. And basically each one of these institutions that we collaborate with has brought very significant instrumentation to us that basically just improves our ability to get science at different wavelength regions, different spectral covers of wavelengths, and combining different number of telescopes together. So it's really enhanced the power of the CHARA Array to collaborate with all these different institutions. At the CHARA Array, we're always looking forward to what the next big step for us will be. One initiative that we're working on is to improve the sensitivity of the CHARA Array. So one aspect of doing this is that we're currently building a new beam combiner in the lab with a high sensitivity camera, basically to improve our magnitude limit and see stars at about 2 magnitudes fainter than what we currently can do. That will open the door to observing a lot more stars in the sky. And we also have a program that will that we plan to add a 7th telescope to the array. And this will be different from our other telescopes. Our current telescopes are fixed in position, and we basically let the stars rotate in the sky, or the Earth rotate, and you can sample different baseline projections of what you're looking at. But what this new telescope will be, it will be a mobile telescope that sits on a trailer and that you can drive around. So we can kind of reconfigure the array at that point using this 7th telescope that we will add. And so we currently have purchased the telescope and are working on building an enclosure. And one novel aspect of this new telescope is that currently with our existing telescopes, we connect them all together and bring the light into the lab through vacuum pipes. And so this new 7th telescope will be the light will be taken into the lab through fiber optics. And so basically this will allow more configurations, because you don't have to build these sturdy vacuum pipes that go across the mountaintop anymore. You just lay some fibers and you can connect the light in. And so this will basically, every pair of telescopes that you observe with gives you a slice of information along that direction of the star. So being able to add a telescope at different locations on the mountain will enable us to get more complete information about what the star looks like. JWST is likely to revolutionize astronomy. And so basically, being in space, you get very crisp, clear images. And JWST has a larger mirror than the Hubble Space Telescope. So you get you can improve your angular resolution. And JWST also observes at longer wavelengths into the infrared. So this basically allows you to peer deeper into the early universe to see the first galaxies that were formed, and also to peer deeper into young star-forming regions. And so basically, you get new visions into the earliest stars that form, and the stars that are currently forming, stars in their planetary systems. So this has I think it has the potential for breakthrough science in many areas.